Okay, so in this lecture, this is going to be a very theoretical lecture, and in this lecture, we're going to be discussing how ClickHouse works under the hood. Now, even before we jump into any of the practical stuff or actually writing some ClickHouse queries ourselves, it is very important that we understand the underlying working procedure of ClickHouse and the merge tree architecture. The merge tree architecture is a very important table engine in ClickHouse, and the working of it is something that you should know before you actually start writing hands-on queries. So this is going to be very theoretical. We're not going to be writing any queries in this lecture, but I'm just going to be explaining the entire working to you step by step in a very simple procedure. So let's get started. So the agenda for this lecture is going to be the following. First, we're going to be discussing the difference between an OLAP and an OLTP database, but with respect to its design in primary key only. We're going to be discussing how the primary key varies with respect to an OLTP database and an OLAP database. And then we're going to be moving into some of the merge tree architecture jargon. All of these things, the sparse index, parts and granules, in-memory sorting, partitioning, TTL clauses, all of this are part of the merge tree engine or the merge tree architecture. And to understand the merge tree even deeper, these concepts are something you should know about. So we're going to be discussing sparse index, parts and granules, in-memory sorting, partitioning, and TTL clause. So let's get into it. Now, we know that in a row-based database system, so a row-based database is usually an OLTP database. So an OLTP database is row-based database. Let's say we have a table like this. This could be something like ID, name, salary, age, so on and so forth. It doesn't matter. Now, how do we define a primary key in a row-based database system? Something like MySQL or SQL or whatever. How do we define a primary key? The way we define the primary key is we select an entire column to say that this column will help us uniquely identify any row in this table. Now let's say I choose two rows. This is row 1 and this is row 2. And if the values in my row are like follows, let's say R1 has 1, comma, Alice, comma, 30,000, comma, age is 30. And then R2 has values such as 2, Alice, 30,000 again, and 30. Now, how do we know that row 1 and row 2 are different entities? Because they are different Alices. But how do we know that they're different Alices through the database? We know that through the primary key. This ID that we have defined to be the primary key tells us that these two Alices are actually different Alices. So what does primary key in an OLTP database help us do? An OLTP database's primary key is focused on making sure that there is uniqueness in the rows. So making sure that the rows are unique is enforced through a primary key in an OLTP database. This is the main important feature or a function for a primary key. And why do we need to ensure uniqueness? We need to ensure uniqueness in an OLTP database to make sure that there is data integrity maintained. Now, if we move to a database like ClickHouse, which is in fact an OLAP database system, then the primary key's function is not to ensure uniqueness in the system. Now you might ask me, Rajat, you said that the whole point of having uniqueness in a database is to ensure data integrity. Now, don't I need data integrity when it comes to an OLAP database? Now, that's a very interesting question. And the answer to that question is follows. Now, in a given project, your question is not, should I either use an OLAP database or should I use an OLTP database for good functioning of my project? No, the question you should be asking rather is how do I use both an OLAP database and an OLTP database for very smooth functioning of my data in the system. So in every project, usually OLTP databases are pipelined in such a way that they pass on the data to an OLAP database. So by the time an OLAP database gets the data, it is already made sure that the data that it is receiving is data integrated already. This is something that an OLTP database already makes sure. So let's see the main functioning of primary keys when it comes to an OLAP database. So in an OLAP database like ClickHouse, the primary key is given by an order by clause. And this order by clause is given during the time of table creation. Let me show you a sample ClickHouse query just to make it clear for you. It could be something like create table users. We have a user ID, which is a string. Then we have a name, which is also string. No, actually, the user ID can be made a unit, a 32-bit integer. Yeah, so user ID is going to be a 32-bit integer. Name is going to be string. Email will have, which is also going to be string. And then we'll have a sign up date as well. So this sign up date is going to be of date type. And now we need to define some parameters. So now we need to decide some parameters that for this table of users. We're going to say engine MergeTree order by user ID. Now, what does this mean, order by user ID? So when you run this ClickHouse command on your ClickHouse server, what happens is that a table gets created, or when you insert some values into this table and then push it onto the ClickHouse server, what happens essentially is that this table with so and so values go into something called a read or write buffer. And inside this read or write buffer, this table is going to get sorted by user ID. And once it is sorted by user ID, then it is going to be written onto the disk. Now, there is a lot of things we need to discuss here. There is sorting that happen in-memory sorting that happens. There is partitioning also, which could happen. There is parts. So these tables are called parts. Then we have granules, which is about 8192 rows. All of these things are to be discussed, and we will discuss them. But for now, let's just understand this much. So the primary key in ClickHouse is there to ensure not uniqueness, but rather to give you the sort order or the order in which your table data is to be sorted. So let's understand this a bit deeper. Let's go and so now let's understand this with a live example. So let's say I have a table in as follows. I have 1, 2, 3, 1, 3, 2, 2, 224, 0, 1, 0, 1, 224, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, 0, 2, 0, 1, login. So let's say we have a table as follows. Now this might look a little shabby, but I'm going to explain this in a bit and it's going to become very, very simple. Don't worry about it. So we have user ID 123132, the 1st of January, the 2nd of January 2024. Then we again have the 1st of January 2024, the 3rd of January 2024, 1st of January 2024, and 5th of January 2024. And then in event type, we have login, purchase, login, logout, login, and purchase. I'm just reading out in case my handwriting is a little shabby. So the order by statement that I have used while creating this table is I have said order by user ID, comma, event date. So what ClickHouse is going to do, it's first going to order by user ID and then it is going to order by event date. So let's do the following. So the first thing that we're going to do is we're going to order all the data by user ID. So when I do that, I'm not going to draw the table, but I'm just going to write the value so that it's going to look a little simple for you. It's going to order like this: 1, 1, 2, 2, 3, and 3. So this one comes first. This one comes first. So this is going to be 2024-01-01. And this is going to be, this row is going to be login. The next one that comes is this one. So that is going to be 2024-01-03. And that was logout. And then the next one we had was this 2, which was this 2. So that is going to become 2024-01-02 and purchase. You can skip over to this time frame if you already have understood how it works, but I'm just going to explain this for the people who are not understanding it. Right? So the next 2 that comes after this one is this one, this 2 over here. So that one is 2024-01-05 and that is purchase. The first 3 that we have is this one. So that one is 2024-01-01 login. Then the next 3 is this one, which is 2024-01-01 again, and that is also login. Am I right? Yeah, login. So in the first iteration, when it orders by order ID, this is what it's going to do. So if you see in this iteration, all my order ID column has been sorted in ascending order. Now you could also say DESC here. You could also say DESC and it would do the exact opposite. It would order from 3 to 1. Since I've not mentioned anything, it's going to order by ascending. So I'm going to have 1, 1, 2, 2, 3, 3 along with its respective rows. So now it's going to order by event date. So now we're going to be ordering by this column, which is event date column. And how are we going to do that? So it's important that you understand this part. When we're ordering by event column, we're not going to order just randomly or we're not going to consider the entire table. We're going to be only consider these things. We're going to be only considering these partitions, which have one, so this partition is of user ID 1, user ID 2, user ID 3. So if we sort the event ID inside the first partition, what we're going to get is we're going to get it's already partitioned by ascending, so it's not going to change anything. It's going to be one, it's going to be the same thing. It's going to be the exact same thing. And then we have the second partition. Now, when we come to the second partition, it's also arranged by ascending. But let's say we had 5 over here and 2 over here. So then it would swap. And it would become 0, 1, 0, 2, 0, 1, 0, 5. This is going to be purchased. This is also going to be purchased. As you can see, this one is also sorted. So it's going to retain the same arrangement of rows. Right. So after this, this is my final table after sorting it by, oh, I'm so sorry. Yeah, after sorting it by the sort ID. This is the table that I have gotten. And now ClickHouse is ready to insert this. So this much ordering, it happens in the read and write buffer when you insert data into the ClickHouse server. After this, this whole part is inserted onto the disk. Now I want you to understand what I just said. I said this part is going to be inserted onto the disk, and that is quite literally what it is also called. So when you insert data into ClickHouse, the part of the data you insert is called part. It's called part. It's a very important jargon that you need to understand while dealing with anything related to ClickHouse or especially the MergeTree architecture in general. So one very important feature of the part is that it is immutable, which means it cannot be changed once it is inserted into the disk. So what's going to happen? Let's say first I insert about 50 million rows, and then I insert about 100 million rows. 100 million. Now I want you to understand that these are the sizes of data that we are dealing when it comes to ClickHouse. ClickHouse deals with these kinds of huge numbered rows. We're going to have not just 5, 6 rows. It's going to be 50 million, 100 million rows. So this 50 million rows, all of them, when you insert it into the disk, this becomes one part and this becomes one part. So every part has 3 important things that you need to know. So once the table has been sorted, what's going to happen next is that, so let's say the table has been sorted. The table has been sorted and it is sitting inside the read and write buffer. Like I just said, once it is sorted, it is inserted onto the disk. Now, before you even insert it into the disk, there is one more step that happens, and that is the first row. The first row of the table is also recorded. And that record of the first row of an ordered table is called sparse index. Now, why do we require a sparse index? We're going to come to that very soon, but this much I want you to understand. So the sparse index along with the sorted table and some metadata also. All of this is equal to one part, and this one part will be inserted onto the disk. After it is sorted, it's going to get appended with the sparse index and the metadata, and all of that is going to be inserted onto the disk. Now, there is some very important thing here. You've not just inserted this one table, right? You might have inserted other data as well. So all of this other data, let's say these both tables or these both of those tables. So when you insert this much of data onto the disk, I want you to understand that there is also other data which is present on the disk, right? We have other parts on the data as well. We are not just dealing with that one particular data. We're dealing with a lot of different parts in that disk. So an important feature of MergeTree is that MergeTree architecture is built in such a way that other parts are automatically merged on the backend or on the background. How does this happen? So two parts here, let's say this part and this part. We'll call this A, we'll call this part B. So A and B are going to get merged. But like I said, parts are immutable. You just can't take A, you can't take B and then merge them and keep them on the disk. That is not going to work. So what ClickHouse is going to do is on the read and write buffer, it's going to copy the contents of A, copy the contents of B, create one more sorted table, and obviously that table will have a sparse index of its own and some metadata of its own as well. Combine them onto another table, make this part another part, which is part C, and part C is A plus B. Copy this back to the disk and delete A and delete B. Now this looks a little messy, but I hope you understand my point. My point is that if we have part A and part B on the disk, and those parts can be merged together, instead of having to deal with a lot of disk overhead, what ClickHouse is going to do is it is going to merge both of these parts. And since parts are immutable, you just can't take part A, part B, merge them and keep them on the disk. So it's going to load the contents of part A onto the read and write buffer, the contents of A, the contents of B, both of them are going to be loaded onto the disk, sorry, onto the read and write buffer. And those contents are going to be used to create another new table with its own sparse index, with its own metadata. Once it is created, it's going to be pushed back onto the disk, and the old part A and part B are going to get deleted. And this is one of MergeTree's most famous, most important features are these background merges. Now I want you to understand one thing. Tell me this. So while this merging is happening here, while this A plus B equal to C process is happening here on the read and write buffer, does that mean in this time, if I insert another part, like I said, parts are first put onto the read and write buffer and they're going to get sorted on the read and write buffer, right? So does that mean that part has to wait? Is there some queue that you have to push this part in so that it waits for A and B to finish happening and then that part enters and it has to wait in a queue or something? No, absolutely not. These are concurrent processes. ClickHouse makes sure that all these processes are happened in the background. That's why I said MergeTree helps merge these parts in the background. These are concurrent processes. New parts can be pushed onto the read and write buffer, and the in-memory sorting can also happen on the read and write buffer concurrently at the same time. They can exist as contemporary processes. There is no problem with that. That is why ClickHouse is so fast. Ladies and gentlemen, this is another example for you. So that is done. Now, what is the whole point of having this sparse index like I was telling you about? What is the need for a sparse index? We're going to be discussing that now. So even before we understand the need for sparse indexes, there is one more concept that I need to touch upon to make sure that you are completely covered with. That to make sure that you're all covered up. And that concept is called granules, like I told you before, granules. So what are these granules? These granules are in fact the smallest data unit which contain typically smallest data unit in a table or a part which contain, let me actually like, which contain 8192 rows, 8192 rows. This number is in fact rows. Now, the need for granules is essentially something called data skipping. The need is data skipping. Now, what is this data skipping? Let's try to understand this. So let's say I, so now let's say we are given a problem as follows. Let's say the query from the user has come back as select star from events where event date greater than or equal to this is the given problem at hand. And while creating the database, let's say that my primary key, like I said, when I say primary key, think order, sort order, sort order. Primary key is event date. That means all my data is already sorted by event date and it's already stored in the disk. So now let's go ahead. Like I said, 2024-02-01. Now, if this is my table in the disk, what ClickHouse does is that it will divide this data into granules. Let's say, for the sake of the example, I have 3 granules. The whole part has been able to be divided in 3 granules. First granule, second granule, and third granule. So the first granule will be from 0 to 8192 rows. The second granule, so this part is from 0 to 8192. This will start from 8193. Will be from 8193 to how much is that? 8193, 8193. If I'm not wrong, if my math is not wrong, it should be 16,380, 384. 384. And so my third granule will be rows from 16,385 to, let's say, 17,000. Now, why is that? Because it need not be necessary that the rows in my database are, in fact, multiples of 8192, right? You might just have 17,000 rows. So this part just has 17,000 rows in total. So this granule has 17,000 minus 16,385 rows. It's not necessary that a granule should be 8192 rows. If the part is lesser than 8192 rows, then a granule size will also be that of the part size, obviously. So now comes the important part. Since all of these dates in my table are already sorted by event date or already sorted by this variable, it becomes very easy for me, which means this rows, let's say we have dates from Jan 2022 to December 2022. And in this rows, we have dates from December 2022, from where it left off, to February 2023. Or let's do Jan 2023. And in this set of rows, or in this granule, we have dates from February 2024 to July 2024. So now what happens? So when my ClickHouse is now searching for this particular query to select everything from my events, what it does is that it goes through the first granule. And as soon as it goes through the first granule and it sees that it starts from January 2022, and when it sees that the next granule starts from December 2022, it knows that it can skip this granule. Because my data that I want, which is essentially the data from 2024, is certainly not residing in my first granule. It'll entirely skip that. So then it will search the second granule. It starts from December 2022 and then it goes up to February 2024. Now we certainly know this is actually not February. Let's say this is Jan. So when it sees that the data in my second granule has data comprising from December 2022 to Jan 2024, it'll skip this data as well. It'll skip the whole second granule. And then it will, since there is only one granule left, it will start querying or it'll start searching for my values from this granule. So that saved us a lot of time, that we were able to skip a lot of data and directly go to the data that is relevant, or the granule that was relevant, or most likely the granule that has our required information that the user is querying for. So this is the meaning of data skipping, and this is a very, very important feature of the MergeTree table or the MergeTree table engine. So now let's go to another important part, which is called partitioning. So from this, it is very easy for you to understand that what the need for sparse index was. I'll give you a minute to think about it. In this example, we have actually covered the need for sparse indexes. Where have we done that? Here, when we are comparing this and this. Now, what is this Jan 2022, December 2022? If you remember, I said the primary key was event date. And I've also told you that sparse index is the first row of an already ordered table. So my sparse index here is what ClickHouse is comparing while querying my data to the user. So unknowingly, I've already explained the need for sparse indexes, and now you know what sparse index is used for. Sparse index is essentially used. So sparse index is essentially used to skip data that does not match a given filter. Rather than scanning an entire data set, it helps you look for data which actually contains the filter that the user is providing us with. Got it? So now that being aside, let's move on to the next topic, which is partitioning. So let's move on to partitioning. So let's talk English. What does partition mean? Partition means splitting up of something, making a whole into parts, converting a big piece of cake into 3-4 parts. That is partitioning of a cake. But what is partitioning of a part or partitioning of a table in ClickHouse? Let's see. So it is nothing but grouping data based on the partition clause or partition based on the partition by clause. Now, why does this help? It helps in very easy moving, archiving, and deleting of data, of large data, for example. Let me give you an example of a command, of a ClickHouse command here. Let's say we do something like create table sales, where we have date of type date, region of type string, we have product of type string as well. Let's say revenue is we'll make it a 32-bit integer. Sorry. And that's it. And now we'll say engine is MergeTree. Partition by, I'll tell you what I'm writing, but first let me finish writing it. All right. So this is my command here. So this is my primary key. And this is my partition by clause. So what happens here is that once you create this table and once you add sufficient values into this table, our table will look something like this. We have 4 columns, right? Our table will look something like this. We'll have date here, region, product, and revenue. I'm just keeping it short, but you get what the point is. So this whole table will be split into partitions. How will it be done? Like I've said, partition should be split by year YYYYMM. So this means it's going to be split based on, let's say the first partition that I make in my table is January's partition, January 2024's partition. So that's going to be 2024-01, which is essentially just Jan 2024. This is the first partition that I'm going to have in my table. And I'm going to have 22402. Feb 2024. Now, these are just examples. I'm just assuming that my data in the table starts from January of 2024. You might have data from any other year, and then the respective YYYMM would be corresponding to that particular date and time. Sorry, that particular date. So on and so forth, you might have data. Now, why does it help? Let's say due to some ETL bug that I've had in my ETL pipeline, somehow January's data has a lot of bugs, or a lot of duplicate values have entered January's data. And now I want to remove it completely from now. I'm going to load it back in later, but for now, I want to completely delete the data. So for this, all I need to do, literally all I need to do is just write one line of command. And what is that one line of command? I just have to say alter table sales. Yeah, alter table sales. We'll make this small. I can say drop partition. What is the partition that I want to drop? I want to drop this partition. Drop partition 2024-01. Now again, The role of partition or the use of partition is pretty much this. Now again, partition helps us move this data. So partitioning essentially just helps us move, archive or delete data very smoothly. So when I run this command, all ClickHouse needs to do is just eliminate this partition from my table. If I did not have partitions, let's say I did not include this clause at all, then what would happen is that, since first of all, what's even more difficult is that it is the order by clause is by region and product. So my data has not been ordered by any sort of a date as such, right? So ClickHouse has to go through every single row, find for data that resides in this Jan 2024, and then eliminate that particular row, which is a very tedious task to do. But now all it has to do is just delete this partition, and that's how you have it. It's done. So it's that simple. That was my point. So now I have told you two basic things. So now it might raise a small confusion. Rajat, you told me that partition divides a table into partitions, but you also told me that granules are also there, which are subsections of 8192 rows. So how does this work? It's a bit confusing. Are partitions and granules coexistent? Well, yes. The hierarchy goes something like this. First, we have a partition. First, we have a partition. Inside that partition, we have a granule. No, we have a part. And inside that part, we have a granule. So this is how the hierarchy goes. A partition can be something like 2024-01, like we just saw. And a part actually has a particular syntax that it has to follow. It would be something like partition. The ID would be 2024-01. And then we have something called minimum block and maximum block, which is something you need not worry about just as yet, but let's say 1, 3, and then the version is also 1. So this would be a partition. This is how a part would look inside the first partition, for example. And granule is just these 8192 simple rows. So now that we've done with partition, let's move on to the last topic in our agenda, which is TTL. What is TTL? TTL is time to live. And TTL it's basically a mechanism where ClickHouse automatically deletes, moves, or modifies data in a table over a specified period of time. Let me give you a sample query. Let me finish this. Table or a column over a specified. So let me give you a sample example for this, a sample query for this. You would write a query something like this: create table event. You have your event details in that table, which is something you need not worry about because we've done this enough number of times. And then we have engine, which is merge tree. We have a partition by clause, and then we have an order by clause, and then we have a TTL. And then we have TTL. So TTL, I'm going to write it something like this. So what does time to live tell you? Let's say I have a data of lot of users, and over time, this data gets accumulated and it becomes too much. I want to move some of my data to a cold storage, as in a data that isn't being too frequently used. I want to move it to a cold architecture, or I could just move it to a backup read like Hadoop or anything of that sort. A backup RAID system, I could move that data to. So I don't want that data to live in my current table and accumulate and then cause a lot of disk space wastage. So if there is a lot of data that is being accumulated, there would also be the problem of latency. Latency would also increase. And the whole point of ClickHouse is to decrease latency. It is to work with lightning speed. So too much data just spoils, the dish. So it is important that we delete data. And how we're going to do that is I'm going to say delete the data after 30 days of it residing in my table. How am I going to do that? I'm going to say event date after 30 days I want it to get removed. And here in this space, I'm going to write interval of 30 days. So what's going to happen is that after an interval of 30 days, my data that is residing inside this table is going to get deleted. Now, why do we want that? Again, to summarize, reduce disk space. That's obviously one. And then apart from that, it's also going to be there to reduce latency. This is what's going to happen. Thank you very much. All right, that's it for now. And we're going to have a few more theory sessions before we actually dive in. So this was MergeTree. I have a little more of theory to cover. And after that, we're going to dive into the hands-on lecture series. Thank you so much. We'll see you in the next one.